So thank you very much for coming and hope you are having a lot of fun and looking forward to all of your interesting talks. And yeah, today I will be talking about this work we posted this like a couple of weeks ago on Yang Li in different dimensions. So this work is done with our very talented and hardworking grad student Eric Argelio, also in the audience, and Igor and Grisha. So yeah, this work is posted on like May the 9th, and we should mark that day, the day of like 3D Yang Li, because on that day we have like three papers showing up on arXiv on this single topic. And I would encourage you to also check the other two papers, which also show that yeah, so you can start from like a different aspect and still get like very consistent results. Yeah, so okay, so the underlying motivation is that okay, so also for this collaboration, we wanted to understand hopefully QCD and more generally like the behavior, the emergent behavior of strongly coupled quantum field theories or like theories of many body, like infinite degrees of freedom. And it'll be interesting, like so these years will be starting to see that like we have like a lot of different methods, like Monte Carlo, like Hamiltonian methods, and we have perturbation theory, we have bootstrap, all kind of like getting more and more dense and start providing us like very accurate results. And different results will start to come in to overlapping regimes and where we can start like checking the consistency across different methods. And in particular, I wanted to kind of like raise some attention towards the Hamiltonian methods, which is a collection of, say, like we wanted to study like the quantum theory of, say, like, so quantum lattice, the lattice spins, or like fermions. And we can also, yeah, so we also have like Hamiltonian truncation of quantum field theories and like known to be like, say, TCSA, truncated conformal space approach, and DLCQ, Lycon quantization, for example, DLCQ, and Lycon conformal truncation. And yeah, so we've been studying, say, DMRG, that's the matrix renormalization group, for like decades. And very recently, there's this model called fuzzy sphere, which is going to be actually the center of this talk. This talk. So we have all of these different methods to kind of like target at a Hamiltonian. So of course, when you when you have like a large degrees of freedom in your Hilbert space and you wanted to diagonalize the Hamiltonian in that very large Hilbert space, then it's kind of like, so people always say that this is very slow, but in a lot of cases, we're gonna see that we'll actually have, so like within our computation power, we start to see that we get like reasonable or sometimes very good accuracy. And yeah, and these methods would be very useful in the case where we don't have very powerful tools from the other methods, say Bootstrap and Monte Carlo. Here I put question mark here because I don't want to say that Monte Carlo and Bootstrap are not good for Yang Li criticality, but certainly when you're with non-Hermitian or non-unitary theories, both Monte Carlo and Bootstrap kind of like don't have their most powerful tool that like people are so like the most proud of. So I'll put the question mark here. And then for Hamiltonian, like for the Hamiltonian method studying Yang Li criticality, this will be good, because this will be like very important, like much more important tool to study the strongly coupled quantum field theory or conformal field theory with some precision. And so our main topic, the Yang Li criticality, is actually, yeah, so it already has like a very long history. So it's first known as, so it is first brought up by Yang Zhenying and Li Zhengdao in 1952. It's been like 70 years old. as a singularity in the zeros in the partition function as a function of the complex magnetic field of the Ising model. So basically, if you start with just like a bunch of spins on the lattice, and then, okay, so if you first, yeah, so if you take the, yeah, so if you take the so if you add a magnetic field, but then the coefficient is complex, then there is actually a singularity. So in the sense that there's a line of imaginary coupling or imaginary magnetic field where you look at the partition function, there's a lot of zeros. So basically, yeah, so you get 0. And then the point where the z is equal to 0 gets more and more dense as you approach this critical coupling. As you approach this critical point. So this point is called the Yang-Lee edge singularity. Is basically saying that the number of zeros, like the number of zeros as well, the density of zeros for say unitary length in the space of couplings is like diverging, and people studied it using say like high temperature expansion. So this is an approximation method, and they reveals that the number of zeros goes like a power law as you approach the criticality. And we can extract the critical exponent. And once you have the critical exponent, you can start asking, okay, so what kind of CFT this is? And Michael Fisher in 1978 proposed that there's a Landau-Ginzburg description of phi cube theory. So yeah, so we know the Ising is phi to the 4th, and here we have like phi to the cube. Yeah, and then in order to avoid, yes, the basically, yeah, in order to stabilize it, we put an I in front, so this is like still a stabilized potential, but then you sacrifice the unitarity. And what can be studied is the 6 minus epsilon expansion of this model. And in this paper, the author studied the mean field theory, and then has a prediction of this sigma critical exponent as a function of the space-time dimension. And the result kind of matches the expectation from the last page, where, yeah, we get it from just counting the zeros from the Yang-Lee edge singularity. So basically, this establishes that the Yang-Lee is described in multiple dimensions, in like various dimensions, is described by this phi cube theory. And then specifically in dimension 2, we know that there's like, so a lot of models are exactly solvable. So this is established by the Mellon, Polyakov, and Zamolodchikov in the 80s. And then these, yeah, so these days we know these models very well. We call them minimal models, MPQ. And so the series P plus 1 is unitary, and everything else in that series is non-unitary. So we have like very complicated or like very, yeah, variety kinds of like non-unitary theories, like much more interesting than the unitary series, I would say. And it turns out that the simplest unitary and non-unitary theories are the Ising and Yang-Lee. So Ising is M34. It's so simple that it only has 2 relevant fields, the sigma deformation and the epsilon deformation. And for Yang-Lee, it's even simpler. There's only 1 relevant field. And this work has been first proposed, was first proposed by John Carnegie in 1985. And then, so what he did is that, okay, so since we have these exactly solvable theories, let me just like plug in delta phi is equal to minus 2/5. And then this gives a prediction. Okay, so there's a relationship between the critical exponent and then the scaling dimension of this relevant field. And this prediction shows that sigma is -1.6. The exact answer is that, and also that matches this mean field result taking d is equal to 2, approximately. So that this kind of like, yeah, this agreement tells us that in 2D, the theory is probably exactly solvable, and then we would know everything exactly. Yeah, so
It's only pretty different.
sorry, what?
To improve the grade.
Uh, yeah,
So the equal 6 and above and below.
yeah, yeah. So you need to study the leading renormalization term. Yeah. The perturbation expansion around them. Yeah, so since we know all of these exact results, it's kind of so basically we can take this approach of like understanding Yang-Lee theory in various dimensions. By the way, I should mention that, okay, so despite the fact that Yang-Lee has been like understood exactly in 2 dimensions, in generic dimensions, since we don't have these exactly solvable models, and also because the theory is non-unitary, so it's kind of hard to directly simulate. So it's not at the same level of understanding as, say, the 2D case, and also like in the 3D is not as understood as the, say, the 3D Ising model. So that's why it's still interesting to study it. It's very simple, but it's not solved. Yeah, and we wanted to understand the dimension, like Yang-Lee in more generic dimensions. We have the 6 minus epsilon expansion, and we also have the exact solution in 2 dimension. So it's kind of a, yeah, so it's kind of a good strategy to put these 2 pieces of information together and start bridging the understanding from different sides. And for the 6 minus epsilon expansion, nowadays we have, like, from many papers, the scaling dimensions of a lot of these leading or lowest operators to very high loop orders. And then what people do with these the 6 minus epsilon expansion is that we can study the Padé approximation, right? And here we study a modified version of the Padé approximation by fixing the scaling dimension in 2 dimension, or in 2 space-time dimension, because there we know the exact answer. So then using this, yeah, so using this approximation, we can extract the scaling dimension of say like the 3 most relevant fields in the game across different dimensions. Here I'm showing the spectrum of the 2-dimensional Yang-Lee. So we'll believe that this picture is roughly the same for like different dimensions. Like the number of relevant operators is not going to abruptly change. So yeah, so this the number of so the spectrum of primaries is actually very sparse. We have identity and we have phi. In 2D in particular, phi is below the vacuum, but that's kind of like a 2D special case. And then we have the stress tensor at dimension 3 or dimension D. And then we have operator that's in 2D we know as TT bar, and in more generic dimensions we know as the phi cube operator. So equation of motion kills the phi square operator. So the next leading or the most relevant irrelevant scalar is the phi cube operator. And then we also have a spinning one. This, yeah, which is called cube. And it has scale, yeah, so yeah, and then we can just keep track of their scaling dimension using the 6 minus epsilon with a 2-sided Padé. And we can see that this line is a very smooth curve. It doesn't have like a lot of ups and downs, and also it's like very close to linear. So that's kind of like encouraging, because this is usually in this way the approximation works better. And the prediction is that in 3 dimension, we're gonna have like delta phi is 0.218. And then the TT bar or the phi cube is, yes, thanks. The phi cube is like 4.6 and Q is also something around like 4.6 or 4.7. And then we also have like the prediction d squared of 4, which we also did using just explicit lattice. Okay, so that's kind of like the expectation from the Landau-Ginzburg series. And what about like a quantum Hamiltonian, right? So our model is basically this quantum many-body theory of there's a bunch of interacting spins. So in 2D, okay, so here, since 2D is most understood, I'll just show an example of like how to study Yang-Lee criticality as a quantum criticality in this Hamiltonian model and how to extract everything. It's particularly since this Hamiltonian is non-Hermitian, how do we deal with it? So this is the Hamiltonian in 2D. This is basically just a one-dimensional, a 1 plus 1D. So it's basically just a one-dimensional periodic spin chain with the nearest hopping term and the transverse field. So the beginning two terms is also known as the transverse field Ising model. And there is the critical point where the theory flows to 2D Ising CFT. But we don't, yeah, so instead of like going to that critical point, we take this coupling to be slightly larger. So in the phase diagram, we're basically taking the temperature to be a little bit above the Ising critical temperature. In other words, we go to the paramagnetic phase or the high temperature phase. And then starting from there, we introduce an imaginary longitudinal magnetic field, which explicitly breaks the Z2 symmetry. And then, so for this non-Hermitian Hamiltonian, a very important fact is that the theory is PT symmetric. So here the PT symmetry means that, so the PT symmetry is a combination of this Z2 we have already explicitly broken, and the time reversal, which takes I to minus I. So if you add this on the Hamiltonian, we flip the Z longitudinal magnetic field, but then we flip I, so the Hamiltonian is invariant. So with this PD symmetry, people have established that the Hamiltonian, at least, yeah, so there should at least be a parameter space where the Hamiltonian has real eigenvalues. And then as we, okay, so and then as we turn out coupling and then across some phase transition, and that, yeah, we will start having spontaneous PT symmetry breaking. In that scenario, so it's like this plot. So the real eigenvalues will collide and merge into a complex conjugate pair. And then the point that they merge is called the exceptional point, where the eigenvalues, the two eigenstates merge into one eigensector. And particularly at that point, the Hamiltonian is not diagonalizable because it's a Jordan form. Yeah, but we're not going to study that point sharp. We're always going to be on this real Hamiltonian, like the real side. Okay, so here's how we study it. We first go to the paramagnetic field, paramagnetic phase, and then we start cranking up the transverse field to a point where we see merging. But instead of hitting the merging, we go slightly back and we try to hit the point where, like, so we try to hit the point where the spectrum looks like a CFT. And then we define that as our pseudo-critical point. It's not the real one because it's still a finite system. And then we take that point and extrapolate it to n goes to infinity. N is the number of sides. And then the criterion that we use to judge whether we have a CFT spectrum is whether the stress tensor is the scalar dimension measurement of the stress tensor is equal to the space-time dimension 2 in this case. And then all of the red, okay, so for that, on that point, we can also measure the scaling dimension of other operators, and then we can extrapolate these scaling dimensions to n goes to infinity, and then we'll have our predictions. And then here, this is our prediction. Actually, this is the I think this is like not extrapolated. This is probably like n is equal to something like 20, I forget exact number. So just for different point on the paramagnetic phase, we can study where the critical point is and then extrapolate, extract a bunch of scaling dimension, the phi, TT bar, and Q phi. And we see that they all kind of get close to the exact number. And then it seems like particularly the theory likes large HX, meaning deeper in the paramagnetic field phase. So this is like a practical lesson that we learned that helps the convergence. But in all of these points, all of these HX, we're supposed to get a critical point in HC where the theory flows to Yang Li. Okay, so now we wanted to take this lesson to 3-dimension. And then in 3-dimension, we wanted to use, okay, so a very important fact about this Hamiltonian model is that we want to use real quantization. In the sense that we want the Hamiltonian to be, we want to put the Hamiltonian on the sphere. So then when we realize the CFT, it will be a finite volume CFT in S2 cross R. And then in that quantization scheme, the energy is the energy levels will be scaling dimension divided by some volume factor. So in this scenario, the volume factor does not break anything. It actually helps us to read off the spectrum of the scaling dimension of the CFT. So we definitely want that. And there's also one-to-one correspondence between the local operators and the eigenstates of the spherical of the spherical Hamiltonian. But how to realize that is kind of like it's kind of an art. So there's no good way. So if we want to put like say lattice sites on the sphere, then we risk breaking the SO3 symmetry, the rotation symmetry. And then of course there's a way to like maximally preserve the rotation symmetry, which is these regular polyhedrons on in 3-dimension, but there are only finite number of them. And actually, it is interesting in its own right to study these models, and we actually studied them. We got like a consistent result. But I just want to mention that this is like the motivation why people start considering the fuzzy sphere. And in the fuzzy sphere, so it's because there's only finite number of these regular polyhedrons. So there's no good way of like taking the thermodynamic limit without further breaking the symmetry. And then people have proposed in recent years this fuzzy sphere model. I'll just say, okay, I'll leave the details, but I'll just say it's still a bunch of fermions interacting. And then there's like a approximate notion of locality, that's the fuzziness. And then as you put more and more the fermions, they become more and more local. So it actually also, it's still kind of like a model of having a lattice on the sphere, just like the position is kind of fuzzy. And then the benefit is that we have exact SO3 symmetry, and also we have, so n here is a parameter, so we can take n goes to infinity. So and each time, for each n, we exactly preserve the SO3 symmetry. So it's kind of like easier to take the thermodynamic limit. All right, so then we study this using the same strategy. So taking the fuzzy sphere model, and then we first go to, so the phase diagram is still this. So we first go to the paramagnetic phase, kind of like go deeper, as deep as possible, and then start cranking up the imaginary longitudinal magnetic field. And then we're gonna hit a point where the scaling dimension of the stress tensor is measured closest to 3, the space-time dimension. And then we take that as our, we take that as our prediction of the scaling dimension. And then we extrapolate these scaling dimensions to the thermodynamic limit. And we found remarkable consistency with the conformal symmetry, meaning all of the descendant scaling dimensions in the scheme will converge very nicely to integers above the corresponding primaries. And we also checked a bunch of like other consistencies, saying like we can measure the scaling dimension using the eigenvalues. We can also measure the scaling dimension using some CFT consistency between 3-point functions using the CFT algebra. And we can also measure a bunch of OPE coefficients using the matrix element of fuzzy sphere. And in the end, we get like a big table with basically everything we can get about the lowest primaries and also this state 4 primary. And yeah, so they are mostly accurate to like say second or even the third digit. So it's like a big improvement from previous methods. All right, so yeah, I also wanted to mention we also studied the Platonic solids, the finite explicit lattice in 3 dimension, and we found the result is like consistent from what we got from like fuzzy sphere. And we also studied this 24 cell, which is like a it's a regular polytope in 4 dimension. And we also get like a reasonable accuracy for the scaling dimension of phi and phi cube from the 2-sided Pade approximation. And okay, so I'll stop here. I just wanted to say that, okay, so we obtained a numerical solution, which is comfortably agreed for Young-Lee criticality, which agrees with the 6 minus epsilon expansion. And in the future, it will be interesting to apply the same strategy for the M3A series, and that which is discussed in Zimo's talk. And it will also be interesting to study, for example, we take this lesson and we study 4 dimension, which is the interesting, strongly interacting CFT. And then there's like larger polytopes, and we can try to study them to get better accuracy. Yeah. All right. Thank you very much.
Questions? I assume you was dealing on in the 2 dimensions.
Yes. Yeah.
Then the other results from
all of them are just actually all of them can be done using just exact diagonalization. Yeah, even in 2D with 20 sides, exact diagonalization can be done on a laptop, and it gives you say like the 3rd digit pretty much. Yeah.
Can I ask a nice question? Why does this non-Hermitian Hamiltonian have real eigenvalues?
It's because of the PD symmetry. I guess, yeah. I don't know the mathematical proof. Yeah, but whenever you have the symmetry, yeah, so the spectrum is real. Yeah. Thank you. Yeah, thank you.
I guess you could say once you speak symmetry and it's at one point you have a real spectrum in order for the spectrum to become non-real to your eigenvalues that collide. So you can feel.
So as you go, eventually, if you go far away, eigenvalues will.
Yeah, they collide and become complex.
Gravity curve, like the right rules that there are all these points of merger and the continuum should be the same. The response is good. I think right?
Yeah.
It's very tough, but when the point close to
that's a good question. So I think it's really the question is like, is there a deformation that is like, say, so is there a non-local deformation of the underlying CFT that is, say, like triggered by the fuzzy sphere? And okay, so in practice, we didn't worry about it, and we diagonalized the Hamiltonian. It seems like everything is reasonable. I think it's very important that so the fuzzy sphere is actually becoming local, becoming local. So yeah.
Stay on local component of like a distance, if you don't want
Yeah, yeah. But then in that case, you will find large deviation from, okay, so we have the stress tensor that's exactly integer, right? So if we find some non-local series, then the stress tensor will be something that's kind of meaningless. We don't have stress tensor, so that's kind of like a smoking gun that we found the local theory.
Just a comment that this of course was first applied to heating model and other unitary models, and there you have this very powerful cross-check with a formal bootstrap.
Yeah.
But for this model, the bootstrap was sort of very fuzzy.
Yeah, yeah.
Like there were results, but they were a bit all over the place, so.
Yeah.
You can only compare, so it's a very interesting application.
Yeah.
That you can only compare with the data set. Yeah, work.
Yeah, so we don't have the usual positive, like semi-definite programming approach. And here, like whatever we mean by bootstrap is basically we pick up the crossing equation, and then we try to just solve them in a truncated sense. So it's an approximation, it's not rigorous anymore. And then and then basically you get some result, and at the end of the day, it has some deviation, but the error bars are not. Yeah.
Yeah, one last question.
Some simulations in the context of statistic which Hawaii models,
Mhm.
they can be interpreted as simulations on a physical background.
Yeah.
Okay, so if you look to block and shift matrices, they satisfy an algebra, so you can probably generating some physical. But if you do this naively, however, this physical background
Mhm.
comes out to be unstable.
Fuzzy torus.
Yeah.
Yeah.
It comes out to be unstable. So classically, it looks fine, but because of the quantum projection, it comes out to be unstable.
I guess it could be like something particular to this torus topology, right? Yeah.
So, for instance, is there an issue like that? What around is the stability?
I think what we mean by fuzzy manifold is not the fuzzy spheres here. It's like the next quantization step that makes obviously the idea means. Yeah, it's not people call fuzzy manifold.
Yeah, here, I guess one can just consider this fuzzy sphere as just a bunch of like fermions on the sphere. But they have some non-trivial wave function, so they have like finite overlap when n is finite. So we do have a spherical geometry. But actually, yeah, I don't really understand like what is the argument for like stability here.
Often the curvature really collect from the scale, right?
Yeah.
The R phi squared.
Yeah, I guess it's probably because the spherical symmetry is like very symmetric, so there's not like a lot of relevant deformation that you can use. You can take to like to break the spherical symmetry, right? And then like if you don't do something drastical, say like you take this hemisphere very strongly coupled the other hemisphere like a zero coupling, and then take the thermodynamic limit, then in the end you should still have a sphere. Yeah.
I just want to make one sociological comment, which is this paper by Van Galen. It was written in 91, and by 2008, first 17 years, by then it had 3 citations. And it's really an amazing paper, so don't be discouraged if your paper is unsighted, right? Then somehow it was discovered in 2009, and now it's like experiencing it, which may go up and up.
Great, let's thank John again.